The Chelyabinsk impactor startled the world. No one saw its terminal approach because it was in the daytime sky, only a few degrees from the sun. In this video, I'll present a solution to avoid more such frights and perhaps even to save lives. Hello everyone, my name is Matthew Sene. I am a professional astronomer. I live in Tucson, Arizona. The near-Earth object detection problem is a serious one because these are dangerous objects and we need to find them before they find us. More properly, the asteroid search radar should be called a near-Earth object search and tracking radar. Most near-Earth objects are asteroids, but comets can be NEOs too. In the 10 to 100 meter size range, NEO population estimates give over 20 million objects. That's a lot to try and find. Earth-based optical telescopes are the primary instruments used in the search for near-Earth objects. Earth-based optical telescopes don't work in the daytime or at night when it's cloudy, and during bright moon nights, their detection limit is degraded. Near-Earth objects can move undetected through the Earth-Moon system in one day. This is what the Chelyabinsk impactor was trying to do before the Earth got in its way. It's evident that Earth-based optical telescopes can't do the entire job of detecting near-Earth objects. What about radar? Radar works with full effectiveness when it's daytime, when it's cloudy, or when the moon is bright. Could radar be of any help to us? Here is what comes to mind for most people when you say radar. This dish is big, but it has a very small field of view, equal to only about 1/20th of the diameter of the full moon. That makes this a tracking radar. It can only track near-Earth objects already discovered by the optical surveys. This next part takes a bit of abstract thought. Schematically depicted in this diagram are a small dish and a large dish. The objects attached to the vertex of each dish are not material objects. They are graphical illustrations of the sensitivity and field of view of each dish. These are called the main beam lobes of each dish. The main lobe of the big dish is longer than the main lobe of the small dish. This indicates that the big dish has a higher sensitivity and can see fainter objects. The small dish isn't as sensitive as the big dish, but the diameter of its lobe indicates that it has a wider field of view than the big dish. The angular diameter of the lobes is measured at the halfway point between the dish and the end of the lobe. This is called the full width half max for people who like technical terms. Now we see two objects above each dish. Because the two objects are within the main lobe of the small dish perceives them as being only one object. The big dish can perceive there is only one object in the beam, but it must rotate clockwise a bit to detect the second object. The small dish would have to rotate clockwise and counterclockwise more than the big dish to perceive that there is only one object in the beam at a time. The small dish will suffer from source confusion more than the large dish. What we want is a large field of view, high sensitivity, and the ability to resolve different sources. With the big dish, we get high sensitivity, good resolution, but we have a small field of view. With the small dish, we get a big field of view, but we don't get very high sensitivity or resolution. Combining the output of many small dishes improves the sensitivity and resolution, but the field of view still won't be very large. And there's the problem of steering the dishes around the sky. We want high sensitivity and a big field of view, but we don't seem to be able to do it with the dishes. Is there a way out of this conundrum? Here is a type of radar that you may never have seen before. Each of those flat faces is called a planar phased array. Each face of the array is 102 feet in diameter. Each face of the array is covered by 5,300 antenna elements. This close-up of an array face shows some of the antenna elements. Those arrays are stationary. They do not move. Yet they have something that a dish doesn't. Each phased array in the picture has a 120-degree field of view. Together, they can keep 240 degrees of the horizon under continuous surveillance. This particular radar is in Alaska. Its job is to detect any intercontinental ballistic missiles launched against the United States. The near-Earth object search and tracking radar would be horizontal, like a tabletop. Here is such an array with many antenna elements. It's forming a beam to observe that yellow object above it. It can also form a second beam to look at a second object. Because this is America and more is better, we have 3 beams, 4 beams, 5 beams, and 6 beams looking at 6 different objects widely distributed across the sky. So this flat, immobile object is doing the same job as 6 dishes like this. How is this possible? How can it do that? It can do this through digital signal processing. It involves a lot of math and some very fast computers. Here is the basic anatomy of a planar phased array. It's composed of individual panels. It's flat. And behind the panels, there are various bits of electronics and fiber optics holding it all together. This small panel has 64 copper patch antennas on the front side of a green fiberglass board. Let's see what's behind the copper patch antennas on the back side of the panel. Here is a patch antenna on a small bit of the panel. The view from above is on the left, and a side view is on the right. That small little gray dot on the patch is supposed to be the top of a little column of solder from the patch down to the backside of the panel. This makes electrical contact between the copper patch on the front of the panel and the little black rectangle on the back of the panel. On the left edge of the side view, you can see a cross-section of the thin copper patch. The little black rectangle is a side view of an integrated circuit that's stuck to the backside of the board. The little integrated circuit package could be a power transistor if the panel is for a transmitter, or it could be an amplifier if the panel is for a receiver. The black wire-like object is an optical fiber that sends control signals to and data from the integrated circuit. Here is a diagram of the panel and some of its biggest components. The panel has electrical power leads. All data would be digitized and carried by fiber optics. I have indicated the presence of a few fiber optic cables. In reality, all the patches would have them. The backplane keeps out interference from behind and helps the patches have greater sensitivity in the forward direction. The box at the bottom labeled MUX demux stands for multiplexer demultiplexer. It acts as sort of a traffic cop to send data to the control room and control signals to the panels, such as a master oscillator signal. This is an attempt to give you an overall view of how the search and tracking radar would work. You can see the transmitter and receiver arrays on the ground and the compass points around them. The light blue area is meant to represent the sky. Here is a section of the sky. The blue dot at the upper right corner represents the cross-section of a receiver beam projected against the sky. The receiver array is capable of forming many overlapping receiver beams simultaneously. Additional rows can also be formed. This section of the sky is now covered by receiver beams. Rather than drawing all these little dots on the sky, I'm going to represent a receiver beam field such as this by a solid blue. The darker blue area is where the receiver array has formed a field of receiver beams to receive any echoes from detected objects. You can see two beams there from the transmitter array. The one on the left is the scanning search beam of the transmitter, and the one on the right is the tracking beam of the transmitter array. The blue beam is from the receiver array to track that green object with the red and blue circles around it. The skinny blue arcs show the 120 degree by 120 degree search region of the sky. Here I have unwrapped the search region from the spherical sky so you can have a better view. This shows the 120 degrees by 120 degrees search field. Have a look at the northwest corner of the search field. There is a little red dot there. That represents the cross-section of the transmitter search beam. You can see that the search beam has just started out, and it has a trailing field of receiver beams. The search beam jumps half a beam ahead at each move. Once it reaches the eastern edge of the search field, the search beam returns west and begins another scan one line south of the previous line. It repeats this action for every scan line in the search field. The search beam has been scanning for a little while. Watch what happens next. Stop the action. Why is that line of sky on top without any search beams in it? The radar has a finite range. The largest object we might want to detect would be about 1 to 2 kilometers in diameter. All of the larger objects have already been detected, but there may still be some 1 or 2 kilometer objects out there hiding where we haven't been looking. The search beam takes a specific amount of time to scan from the beginning up here to the end down here. The maximum time delay from the transmitter to the object to the receiver corresponds to the greatest range at which we could detect a 1 or 2 kilometer object. Just a little bit of math here. On the left edge of the diagram, you can see the transmitter sending radar energy to the object and its echo being detected by the receiver. The time it takes to do this is the round trip time from the transmitter to the object to the receiver. We need only half of this time to calculate the distance to the object. The radar waves move at the speed of light, so we have to multiply half of the round trip time by the speed of light to get the distance to the object. The units are easy to understand. For example, if you drive at 10 miles per hour for 1 hour, you will have traveled 10 miles. So the round trip time delay is what governs the width of the receiver beam field in the north to south direction. If the range of the radar was less, the receiver beam field width would be less in the north-south direction. If the detection range were greater, the width of the beam field would be greater in the north-south direction. Whatever its width, the receiver beam field moves from north to south across the sky. Skipping ahead, we see there is a little green dot in the receiver beam field. This means that the radar has detected an object. We know how long ago the search beam went over that area, so we know the time delay, and then we can calculate the distance to the object. There is a red annulus around the object to show that we are illuminating it with a transmitter tracking beam. The transmitter array can generate two beams simultaneously, one for searching and one for tracking. The active receiver beam field following the transmitter search beam has moved along farther south. But we haven't forgotten about that object. The blue annulus is to indicate that we have formed separate receiver beams to receive the echoes from the transmitter tracking beam for that object. This is the unwrapped version of the first view that we had of the radar. The receiver search beam field is wrapping around to follow the transmitter search beam for another sweep of the search area. The arrays are also still tracking that object that was discovered earlier. The receiver beam field has completely wrapped around as the scanning continues. What happened to that object that was discovered earlier? Well, it has moved out of the range of the radar. However, we got some excellent data on it, and I'm happy to say that it's not going to hit us. Radar can also be our crystal ball to look ahead in time. The tracking data will tell us an object's distance, velocity, and size. We can then establish an object's orbital parameters to determine if it will be a threat. The tracking data will also allow us to confidently predict where an object will be in its orbit for at least 100 years. So the radar will help us on two timescales. One, is anything going to hit us now? And two, will something hit us far in the future? The transmitter and receiver arrays would be more than 200 meters in diameter. The total power necessary to run both the transmitter and receiver arrays would be in the range of 10 to 20 megawatts. So you think this is all too much? The arrays are too big and use too much power. Well, why don't you ask this guy about it? He would probably disagree with you. The total power necessary for a worldwide network of radars is probably a small fraction of that expended in Bitcoin mining. Let's mine a little safety for ourselves. Near-Earth object search and tracking radar is a very important and necessary component of our strategy to protect ourselves from cosmic impacts. The radar will be our last line of warning. For full coverage, there should be 3 of these radars in the northern hemisphere and 3 in the southern hemisphere. The arrays will allow us to see all the NEOs in a sphere centered on the Earth with a radius of a few lunar distances. The least capable system that I would consider deploying would have detected the Chelyabinsk impactor at a range of 2.25 lunar distances. This would have given 16 hours of warning time to those in the impact zone. It was a small impact zone, so people could have walked away at a leisurely pace. To get this project started, there are a few things that I would like to have. I would need money for some consultants. It's always good to hear what the specialists have to say. I would like to construct some prototype array panels. Once the problems are solved for one panel, they're solved for all the panels in the array. I will need to buy some materials and equipment to construct the panels. I'll need some electronic test bench equipment. This little machine is good for making prototype circuit boards. As always, there are mechanical parts that need to be made. This is what I need now, but the next step would be small prototype transmitter and receiver arrays. But it's not time to worry about that yet. Let's build some near-Earth object search and tracking radars so we can see what is lurking out there in the deep, dark depths of space. Thank you for your time and attention. I'm sure you realize by now why we need these radars. The species you save may be your own.